Let's dive right into this explainer, mapping out exactly how quantum particles completely refuse to play by the rules of our everyday reality. If you've ever felt like the universe has a hidden, bizarre layer of logic, well, you're absolutely right. Today, we're zooming way, way in to explore the microscopic rebels that make up everything around us. And more importantly, we're going to see exactly how their behavior defies, well, pretty much everything we thought we knew about physics. Don't worry if any of these concepts sound a little intimidating at first. Here's our map for today. 1. When classical physics failed. 2. The rules of quantum particles. 3. Bizarre quantum behaviors. 4. Tech powered by quantum. And 5. The uncharted quantum frontier. Let's get going. Section 1. When classical physics failed. To really get the quantum world, we've got to travel back to the late 1800s, a time when our traditional understanding of the universe completely broke down. Think about it. According to classical physics, the very atoms that make up your body shouldn't even be stable. Basically, electrons were supposed to continually radiate their energy and just instantly crash into the atomic nucleus. But you haven't collapsed into a microscopic dot, right? Obviously not. This glaring contradiction forced scientists to hunt for a completely new, deeper model of reality. Enter quantum physics, where energy is actually quantized and light can act like a stream of tiny particles. And the collapse of the atom wasn't the only headache. Physicists were wrestling with some seriously unexplained mysteries. For instance, when light shines through gas, that gas absorbs and emits only very specific frequencies of light. We call this atomic spectra. Classical physics? Absolutely no explanation for it. They were also seeing these totally unexpected distributions of light from hot objects, known as black body radiation. And then there was the photoelectric effect, where literally shining light on certain metals actually knocked electrons right off of them. These weird clues, especially the photoelectric effect showing off particle-wave duality, proved that the macroscopic rules we were used to simply did not apply to the microscopic world. Which brings us to Section 2, Rules of Quantum Particles. So, if the old rules didn't work, what are the new rules governing these tiny quantum rebels? Let's take a look. Under these new quantum rules, particles behave entirely differently. In fact, in the math of quantum mechanics, all particles are described as waves by this concept called a wave function. The way this wave evolves over time is mapped out by the famous Schrödinger equation. But here's the crazy twist. We never actually see these quantum waves. Nope, all we ever physically detect are the particles themselves. Instead, we use math, specifically a calculation called the Born rule, to figure out the probability of where that particle might be hiding based on the wave. And this brings us to a seriously mind-bending reality. Because we have to rely on this wave function, it means the universe itself is fundamentally probabilistic. Instead of the exact rock-solid certainties we're used to in everyday life, like calculating exactly where a baseball is going to land when you throw it, the quantum universe only gives us the odds of an outcome. We literally can't know exactly where a particle will turn up until we actually look. This probabilistic nature leads directly to the Heisenberg uncertainty principle. Quantum objects simply do not have definite values for certain pairs of properties at the same time, like their position and momentum. Think of it kind of like taking a photograph. If you take a crisp, clear snapshot of a moving particle, you know its exact position for sure, but you have zero information about its momentum, how fast it was going or in what direction. If you take a photo with motion blur, well, now you know its momentum, but its exact position is totally uncertain. And as Bell's theorem later proved, this uncertainty isn't just some glitch in our cameras or measuring tools. It's a fundamental, baked-in rule of the universe. Another foundational rule here is energy quantization. Actually, this is exactly where the quantum in quantum mechanics comes from. Particles, like the electrons in an atom, can't just have any random, continuous amount of energy. They can only vibrate in certain specific modes. It's a lot like the specific vibrational modes of a guitar string. You get certain distinct notes, not just a smooth sliding scale of every sound possible. Because of this, particles have a minimum zero-point energy. Breaking all those old classical rules, they can't just fall to the bottom of the atomic bucket and crash into the nucleus. There are simply no off-key sliding notes allowed in the quantum realm. Moving on to Section 3, Bizarre Quantum Behaviors. Now let's see how these foundational rules create some truly mind-bending physical phenomena. This is where particles really show off just how differently they behave. So every particle in the universe falls into one of two behavioral categories based on a quirky property called spin. First up, we have bosons. Bosons have integer spin, and they love to share space. They can all exist in the exact same quantum state at the same time. On the flip side, we have fermions, which have half-integer spin. Fermions absolutely refuse to share the same state. That's a stubborn behavior, governed by the Pauli exclusion principle. It's basically the difference between a crowded dance floor where everyone's bumping and overlapping freely and a strict movie theater where everyone demands their own specific assigned seat. Then we have superposition. This is the property where a particle has a probability of being in many different states, literally like being in two different places at the exact same time until we measure it. And yes, this is exactly where the famous, totally absurd idea of Schrödinger's cat being simultaneously alive and dead in a box comes from. But superposition is actually completely natural if we just remember that these particles are acting as waves. Just think of any point on the surface of the ocean. It's essentially a superposition, a combination of thousands of overlapping waves all happening at once. But wait, why don't everyday objects, like cats or cars, act like overlapping waves? Well, the answer to that is decoherence. Decoherence is the ultimate quantum party crasher. The moment a delicate quantum system interacts with its wider environment, or, gets measured by us, its coherent wave-like behavior is instantly lost. Poof. That's the firm boundary line taking us from the weird microscopic quantum realm right back into the macroscopic physical world we actually live in. Next up is perhaps the wildest behavior of all, entanglement. This is where the wave functions of two or more particles mix together, becoming a single quantum object. This introduces the totally baffling concept of non-locality. It means their properties remain instantly correlated, even if you separate those particles by millions of light years. It proves, yet again, that particles simply do not care about the physical distance rules of our everyday macroscopic world. And the rule breaking doesn't stop there either. Because a particle's wave function can penetrate barriers, we get something called quantum tunneling, meaning these particles can effectively walk right through solid walls. I mean, who needs doors in the quantum realm, right? We also see collective behaviors like superconductivity, where electrons move with absolutely zero electrical resistance at low temperatures, and superfluidity, where fluids flow with literally zero viscosity. From phasing through walls to completely frictionless flow, these particles continuously defy classical logic. Section 4. Tech powered by quantum. Now, you might be thinking this all sounds incredibly abstract, just a bunch of complex math and invisible waves. But these bizarre behaviors are actually powering the modern world you live in right now. The reality is, every single time you use modern technology, you're directly harnessing these quantum rebels. Lasers use stimulated emission to create those unified beams of light. Atomic clocks use specific transitions in atoms to keep incredibly accurate time, which is actually the exact foundation of your phone's GPS system. The solid-state transistors in the computer or phone you're using right now, and the LEDs lighting up your screen, they all rely on the quantum band theory of solids. Even in hospitals, MRI machines rely on giant superconducting magnets and incredibly sensitive quantum sensors. These properties are also unlocking the future of computing. Instead of classical bits that are strictly either a 1 or a 0, quantum computers use quantum bits, or qubits. Qubits utilize those bizarre properties of superposition and entanglement to explore an exponential number of states all at the exact same time. The grand challenge right now? Engineering large groups of qubits that can actually stay coherent, dodging that pesky decoherence we just talked about, long enough to do the math. If we can master this, it's a real game changer. It could allow us to simulate entirely new materials and solve impossibly complex biological problems, like protein folding. Section 5. The uncharted quantum frontier. Finally, let's explore the absolute edges of our map, out where our current understanding hits a solid wall and theoretical physics takes over. Right at the center of the unknown is the measurement problem. See, the laws of quantum mechanics tell us a lot, but they totally lack an explanation for what actually happens to a wave function at the exact instant it gets measured and turns into a particle. Since we have this massive gap, we're left with various interpretations of reality. There's the traditional Copenhagen interpretation, the mind-bending many worlds theory, and the pilot wave theory, among others. But here's the catch. They're really just interpretations, because we currently lack the physical experiments to prove which one is actually true when a measurement snaps a particle into place. Another massive frontier is reconciling our two absolute best theories of the universe. On one side, we have quantum field theory. It's the most comprehensive description of microscopic reality we have, forming the standard model of particle physics. But it completely ignores gravity. On the other side, we have Einstein's general relativity. It beautifully explains gravity for large planets and stars, but it entirely breaks down at the quantum level. So, theoretical physicists are desperately hunting for a grand theory of quantum gravity, like string theory or loop quantum gravity, to finally unite the heavy, structured, macroscopic world with these rebellious, unpredictable, microscopic particles. I want to leave you with a final, provocative thought about the quantum realm and the measurement problem itself. Is the wave function a tangible, real physical thing that actually exists out there in the universe? Or is it simply a statistical tool, just our absolute best mathematical guess to describe things that are way too small and way too strange for our brains to fully comprehend? As we chart this quantum universe, are we actually mapping reality, or are we just mapping the limits of human knowledge? Thanks for exploring this explainer with me. Keep questioning the rules.